Hello and welcome everybody to your second week of the Networking Certification Essentials short course with IT Masters and Charles Sturt University. Thank you very much for joining us this week. As always, if you missed last week, that information will be available. The recordings and all of the information, course readings, etc., will be available on your student portal, as well as the recordings will be available on YouTube as well. My name is Jack Stewart. We are joined by the wonderful Ian Robertson, one of our IT Masters mentors, as well as Lily Nguyen, who is helping us make sure everything runs smoothly. Before we get started properly, I'm broadcasting to you tonight from the lands of the Wurundjeri people of the Kulin Nation, whose sovereignty was never ceded, and IT Masters pays our respects to their elders and ancestors and honours an ongoing unbroken connection to lands, waters, and culture. Ian is joining us tonight from Tamaki Makaurau in Auckland, New Zealand, Aotearoa. And we'll start off tonight, just really brief introduction to Ian, who is one of our wonderful mentors. He actually has multiple master's degrees from IT Masters and Charles Sturt University. He's got Information Security and IT Management Masters and is currently studying an MBA. So truly a testament to master's educational opportunities that can be available to you, because he's also worked in the networking space for over 25 years for a variety of different vendors and in IT security. And he also teaches several cloud-related subjects in our full-length full-length courses in the graduate certificates and masters. So just a little bit of housekeeping before I hand over. As usual, if we are able to keep the Q&A to questions related directly to the course content. So that is the actual delivery that Ian is providing. So questions for Ian. We'll have several short Q&A sections during the webinar. Unfortunately, we won't ever be able to make it through all of your fantastic questions, but that is exactly what the forums are for, which are accessible via the student portal. If you'd like to discuss with your fellow participants and suggest ideas and make comments, please feel free to pop that in the chat section as well. And further questions about the administrative side of things can be directed to shortcourses@itmasters.edu.au, where Lily and our wonderful colleagues will be able to answer, hopefully, all of your questions. So without further ado, I'd like to hand you over to Ian. Take it away, Ian.
Thank you, Jack. Yeah, so good to see you all back again for week number 2. This week, we're going to be focusing predominantly on layer 2. So last week, obviously, we spoke about the networking layers, the OSI model, and so on. So this week, we're going to specifically focus on some elements of that layer 2 packet transport layer. Now that includes spanning tree, that includes LACP or link bundling, and it'll also include VLANs. So obviously ask some questions along the way, and I'll take some natural breaks along the way and we can talk about it. Obviously, let's go back a little bit. We talked about this a little bit last week. Historically, we used hubs for sort of computer-to-computer immediate communication. They are layer 1 devices we described last week. They tend to be quite slow. They're prone to what are called collisions, and they provide a single broadcast domain. Bridges, basically an evolution, allowed you to connect 2 hubs together, allowed for a single broadcast domain, but allowed you to have as many collision domains as you had hubs. So diagram-wise, that's essentially what a hub-to-bridge link might look like. So if you imagine those 2 orange boxes as separate buildings or separate floors within a building, you might, in a legacy network, have used a hub or maybe a couple of hubs to manage a floor or to manage a small building. And then you might connect multiple of those floors or small buildings together using a bridge. A few people asked last week the difference between a bridge and a switch, and that's really where we get into this. So essentially, a switch and a bridge provide many of the same functions. Their intention is to separate out those collision domains. The difference is a switch will typically have more than a couple of ports on it. It'll have 24, 48, maybe even several hundred, depending on the size and shape of the device in question. And just as critically, instead of being, one collision domain per hub connected to it, you've got 4 possible collision domains in this particular diagram. That is 1 per device. Now that's actually not, this diagram I realized when I was putting it together is not actually 100% accurate, because this is where we talk about full duplex communications. Full duplex means that 2 devices on the one link can talk at the same time, which essentially means that you've got 8 possible collision domains here. You've got 1 per port facing towards each PC and 1 per PC facing backwards as well. Essentially meaning that the switch can talk to the PC and the PC can talk to the switch concurrently with no risk of them talking over each other. Different types of switching. Essentially, switches these days, modern switches are pretty powerful devices, and there are different ways to address mechanisms of transporting data through a switch. The most common traditional way is what's called store and forward. And what that essentially means is that when a device, say a PC or a server or a printer, wants to talk to something else, it'll send a packet of data. The switch will receive that whole piece of data, that whole packet. It'll process it, it'll analyze it, it'll look for any errors, it'll look for what's called a frame check sequence before deciding whether that data is in fact good and sending it on. That slows things down a little bit, but it does lead to reliability. It means that the only data that goes from device A to device B across that switch is going to be in good order and condition, because anything that's been corrupted, say by a bad link or a bad network card, is going to get thrown out by the switch. That lack of performance, though, isn't great in a data center, where typically you do have very tight controls over reliability and so on. So a more modern approach is what's called cut-through switching. What cut-through switching means is that essentially as soon as it's read enough of the start of the frame to know where to send the data, it sends the data that way. So that's often used particularly in the finance industry for high-frequency trading to significantly improve the rate at which data moves from device A to device B. The trade-off, which is potentially corrupted data being sent through, isn't so important, because if you remember last week when we talked about TCP, there's a lot of checks and balances built into TCP in particular to ensure that corruption is dealt with at higher layers. And then there's fragment free, which essentially takes the cut-through concept a little bit further, and essentially, looks at the first 64 bytes instead of the first 4 bytes, and from there can go, yep, this is good enough. We know that this is going to be a reliable packet or a reliable frame at this time, and we're going to send it on accordingly. Okay, going back, what is a switch designed to do? Its job is to forward Ethernet frames. Now, at layer 2, an Ethernet frame in the Ethernet world is the smallest logical data unit, the smallest piece of data that can be sent across a network. Now, an Ethernet frame consists of a header and then a payload. The header is the information the switch uses. The payload is whatever information you want to get across the network. Now, it uses MAC addresses, which are a layer 2 physical address of a device, to determine how to get information to where it needs to go. That really means that a switch only has 3 things to decide. It needs to know when to send data on and where. It needs to know when not to send data on, and we'll get to that in the next couple of slides. It needs to learn that information by examining the SA, the source address. And it's important to note that the only way a switch can learn where it's got to send data from is for the device that needs to receive that data to first have sent some data. And we'll get to that in a minute, because it's important also to understand that this is where a lot of the problems come from in terms of things like network loops. And that gets us to the next point, which is we want to make sure that when we build up a network, we are building it in a reliable way. We're building it in a way that is has suitable levels of redundancy, so that if there is an interface failure, or what I like to call backhoe fade, somebody puts a backhoe through a network link, the network can continue to function. We need to be able to deal with all of that, but we also need to make sure that when there is unknown traffic on the network, we're not causing what are called loops. And we'll be talking about that and some of the techniques that are used to deal with that tonight. So filtering or forwarding, as I said on the previous slide, switches, one of the main functions they have is to determine when and where to send traffic. So every device that is connected to a network has what's called a MAC address, a media access control address. And that basically is a unique address to that device that allows that device to be able to receive traffic. Now, the first time a device talks to a switch, that switch will learn that MAC address and record in a table called the MAC address table where that device is physically located, as in which port is it connected to. When a frame is received, it looks at the destination address, it looks that up against the MAC address table, and using that information decides which port a particular frame is destined for. So if the MAC address exists, it'll be sent out that port and filtered everywhere else. If it doesn't exist, and you might remember last week I talked about turning switches into hubs, if the destination address does not exist, then the switch's default behavior is to send that frame everywhere, to broadcast it. In other words, to treat it the same as it would a broadcast frame and make it available to everybody everywhere. Now, obviously, and we'll talk about how loops form, that can be a potential problem. If the device that you're trying to send the traffic to doesn't actually exist on the network, and you've got two switches that are connected by two different links, and their default behavior is to send unknown traffic down one link and then back along the other, that is the very definition of a loop. And I've actually got some diagrams in here that I'll get to in a moment. That's essentially what forwarding looks like under normal circumstances. Fred wants to send something to Barney. Fred will send a piece of traffic with that destination address. That's a MAC address. This is Barney's MAC address. On step one, traffic comes in. We know that Barney lives over here on port F02, so that traffic is just sent straight there. It's not sent to Wilma or Betty because that's not their MAC address. And in this case, it is assumed that Fred and Barney's MAC addresses are already known to this switch. And in fact, you can see this in the MAC address table. These 4 MAC addresses, these 4 devices are all known, and the ports are known that they're connected to. So for traffic from Fred to Barney, there can be no loop. There can be no inadvertent receipt of that data somewhere else on the network. Doesn't mean that Fred can't cause a broadcast storm, and we'll talk about that in just a moment as well. So how do we build out that MAC address table, which is this piece down here? Essentially, every time a device talks to a switch, its source address, in other words, the address of the device that sent the data, is learnt by that switch. And so that then builds up that MAC address table, and that table is then persistent for an amount of time. Obviously, there's all sorts of mechanisms that can be used to age that data out, but essentially that switch remembers that that's where those devices are located until such time as better information comes in. So here's an example. We've just turned the switch on for the very first time. Initially, its address table will be empty. The very first time that Fred sends a packet to Barney, the switch will do two things. First, it will learn Fred's address. Okay, I now know that Fred is on port F01. This MAC address exists here. It will also, at the same time, because it doesn't yet know where Barney lives, it will send that frame out to Wilma, to Betty, and to Barney. Now, all three of those will receive that one frame, but only Barney's going to respond. And when Barney responds, the switch now goes, aha, right, now I know where Barney is as well. Still don't know where Wilma or Betty are. They haven't been learnt yet because they haven't spoken to anybody yet. But at least at this point, we now have the ability for these two to talk. And at this point, Barney's reply to Fred is not seen by Wilma or Betty because the switch at step 1 learnt Fred's address. So as they build the MAC table, they'll automatically start ceasing to send traffic unnecessarily. So essentially, when you first switch your switch on, it's a great big hub. And then over the next few minutes, as devices talk to each other and start to establish communication, the amount of that broadcast traffic drops, and the switch starts to behave more and more like a switch rather than like a hub. The exception is there is always a certain amount of what's called broadcast or unknown unicast traffic on a network. So broadcast means anything that is indeed destined for everybody else on a network. So there's all sorts of protocols that use this to their advantage. There's DHCP, which is used to allocate IP addresses. There's certain protocols built into Microsoft Windows that send broadcast traffic all the time as a perfectly normal part of their behavior. And that will continue to be sent out everywhere all the time. Unknown unicast just means a device is trying to talk to something that hasn't yet been seen on the network. And then there's also multicast. Now, for these purposes, and certainly for the purposes of the exams, you can more or less treat multicast the same. The associate level exams don't go into a lot of detail on some more developed multicast capabilities. They're in the advanced exams, as it were. So essentially, broadcast and unknown unicast are the two types of traffic that you need to concern yourself with from an exam point of view. Okay, very quickly, are there any questions before we move on?
We do have a couple.
Yeah, I was just looking at those.
Absolutely.
So,
would you like to take?
Yeah, sure. I'll actually take them both. So how do we add the destination address? So the destination address in a packet or in a frame is actually added by the device that originally sent the original frame. So if, in the case of the earlier example, if Fred wants to talk to Barney, Fred already knows what Barney's MAC address is. There's protocols called address resolution protocol that help that process occur. There's also the ability to define such statically, and in some cases you might actually want to do that. And the switch doesn't have any part in determining that destination address. It's different when you cross a router. We'll talk about that next week. But essentially it's done by the network stack, the operating system of the sending device automatically. And Shebakaman talks about, can you have a switch connected to another switch? You can, absolutely, and we'll actually talk about that because it's important from a loops point of view. And the destination address is always going to be your ultimate destination in a layer 2 network. It's always going to be the destination PC. So in the Fred to Barney case, if there were 2 or 3 or 4 or 10 switches between the two, it's still going to be Fred talking to Barney. The destination MAC address in layer 2 will not change. And Paul asks an excellent question about what happens when the port changes to a new port. So initially, the traffic essentially disappears off the network. So the switch obviously doesn't know automatically that you've unplugged the PC and plugged it in somewhere else until that PC or that device actually sends some traffic and lets the device, the switch, learn the new MAC address location and erase the old MAC address location from its table. Switches will only store a single MAC address against a single port at a time. So you won't have the situation where the old MAC address location and the new are known at the same time. It's either or. So when that happens, that MAC address table will get updated. Now, on devices like Cisco switches, you will actually see a log entry called MAC flap, which basically indicates a potential loop as well. Move on now. Sorry to those whose answers I didn't quite get to.
Everybody started asking so many questions. This is
That's all
fantastic
good.
engagement.
That's all good. Any questions that I don't get to, I'll try to loop back and answer in the forums as well. Some of them, though, I can see I will actually be answering as we move forward. So obviously, if a switch sends everything that it doesn't know out every port, except the inbound port, you've got a potential problem. Because if you've got a network topology, and I'll show one shortly, that has two switches connected to each other by way of two links, it doesn't take long for something unknown to come in on one switch and then get looped back to the other, and then have the process repeat until the entire network link is carrying nothing but garbage traffic. Now, why would you want multiple links between switches? Well, put simply, links fail. You can have interfaces fail. You can have, as I said, somebody putting a backhoe through a data link. It happens a lot, unfortunately. You can have all sorts of issues that might render a physical link between two switches faulty. So good practice is actually to have redundancy at the physical layer, as in the cabling. Now, the problem is, though, loops basically render those links useless. This was identified basically as soon as switches became a thing. And a protocol called spanning tree protocol was very quickly invented by a lady by the name of Radia Perlman, who basically identified a mechanism and a protocol to address this, which very quickly became part of the IEEE standards, which define Ethernet. What does that look like? So here we've got a network topology. Now, each of these switches, for all intents and purposes, can have multiple devices connected to it. For simplicity's sake, we're showing one PC and we're showing one datagram represented by an envelope and what might happen with a loop. Now, I'll play this little animation a couple of times because I'm not sure how well Zoom will record it. But basically, let's say this PC is trying to talk to another PC or another device on the network that, to all intents and purposes, does not yet exist. So it sends its traffic to switch 4, sends it the switches, send it on. Oh, what switch 4's got it again, sends it on again. That's a simplified version of what happens in a loop, except that it doesn't stop after 2 loops, it goes on forever. There's no mechanism for a switch to determine that it's seen a particular frame before, so the traffic just goes on and on and on, and at typical link speeds between switches, it's not long at all before the switch is doing nothing but forwarding that traffic to itself, essentially. That's bad. You know, there's no way around that. That is not a great situation to be in, and essentially means that the very thing you're trying to achieve, which is redundancy, is working against you. Into spanning tree protocol. So this is a relatively old protocol. It's been around a long time. It's absolutely still in active use today. Being an older protocol, you have to remember when you're configuring it and dealing with some of its foibles, it was designed to deal with switches that are a lot slower than your average pocket calculator is today in terms of computing power. So a lot of the design decisions that were made on the assumption that the switch did not have a significant amount of computing power that it could dedicate to performing a form of routing, if you will. So essentially, it aims to do a couple of things. It aims to figure out what the network topology looks like, and then it aims to use that information to figure out which links to cut so that you end up with no loops. You end up with what's called a loop-free topology. And again, it comes back to the fact that a switch's job is to send everything out everywhere that it doesn't recognize. So the standard is called IEEE 802.1d. There's a few different versions, but the main version you'll see in the exams is the original and the best, if you will, 802.1d. There's a few other more modern mechanisms that I'll touch on very briefly as well, but spanning tree is the important one to understand. And essentially what they do, switches will talk to each other, they'll figure out how they're connected to each other before they allow any quote unquote real traffic onto the network. And once they've done that, they'll figure out which links to shut down, to block, to treat as redundant links that can be reintroduced to the network in the event of a failure and not before. There's a few different versions of spanning tree. Now, actually, if I go, there are diagrams for this as well, but if I go back to this example, spanning tree, for example, might determine that the link between switch 4 and switch 5 is redundant, is not currently required, and would potentially break this particular loop by blocking that link, by shutting it down. And doing that, it prevents the loop, but it still means that if then there's a breakage between, say, switch 2 and switch 4, that link can then be re-established and all of those switches can still talk to each other. You don't end up with any isolation in the links. Okay, so there's a few different versions of spanning tree. One of the deficiencies of the original 802.1d spanning tree is that it is very, very slow to do its thing. It can take nearly a minute to make a decision amongst the switches to as to which links should be shut down. And obviously, if you then have a link failure, it can take up to a minute to figure out what to do about that. Now, back when spanning tree was first put together, that probably wasn't considered such a bad thing, but most people these days who might have, say, voice telephony or Zoom calls aren't going to tolerate a network outage of 1 minute in the middle of the business day. So there's newer versions. There's a version called Rapid Spanning Tree, which gets its thing done in more like 2 seconds as opposed to nearly a minute. And then there's versions that allow you to do things on a VLAN by VLAN basis or on a group by group basis. There's other ways you can avoid loops though as well. We'll talk about layer 3 next week, but a common strategy these days is simply not to use a pure layer 2 network, to run layer 3 all the way down to the edge. There are new standards. There's a standard called TRIL, Transparent Interconnect of Lots of Links, which was actually invented by Radia Perlman as well, which takes advantage of the fact that modern switches are actually pretty powerful things and do actually have the ability to be a lot more clever about how they identify loops. And indeed, in the case of TRIL, it allows you to use all of your links active all at once, all the time. And then there's a variation on that called shortest path bridging, which achieves much the same thing in much the same way. But like good standards everywhere, there's of course more than one to choose because of course there is. And then there's a concept called loop protection. I said earlier that switches have no mechanism to determine whether they've seen a particular frame before. Now, that is still true, but some switches can get around that by sending a frame that only they could have created. And if they see their own frame come back at them from a different location, well, by definition, there's a loop there, and they can take steps to protect themselves from that without necessarily using spanning tree. These tend to be non-standard. The advantage of spanning tree, of course, is that it'll work if you've got a network that has, say, Cisco and Juniper and HP and Dell and any other switching vendor you might care to mention, because it is an IEEE standard. Loop protection, on the other hand, tends to be vendor specific. So if you've got a network that's all built around Cisco, you might be able to use their version of loop protection. But if you then introduce, say, a switch from Juniper, you might not. The important thing from an exam perspective is that spanning tree is the protocol that's examined the most, as it were. And there's a reason. The big reason for that is that while it is quite old, it's also very well proven, and it is extremely well supported across the industry. How does spanning tree do this? It uses what is called bridge protocol data units. There's that word bridge again. I mentioned last week that the word bridge and switch are used interchangeably in the standards. It uses those to determine how data gets around. These aren't an IP packet. These are an Ethernet frame. They don't include any IP information at all. And basically, switches will send these special frames every 2 seconds everywhere with the express intent of identifying other switches on the network. Now, to do that, they use a MAC address that happens to be multicast that by default other switches are going to send to everywhere all the time. Switches will recognize this MAC address, though, as being spanning tree and will therefore treat it accordingly. I said it before, there are other versions of spanning tree. There's common spanning tree, which was a Cisco implementation of 802.1d that isn't quite compliant with the standard. There's per VLAN spanning tree, and I'll mention briefly in a couple of slides why that might be important. And there's what's called PVST plus enhanced per VLAN spanning tree, which essentially is again a Cisco extension that allows common spanning tree to interoperate with per VLAN spanning tree. Generally, the only time you'll ever see that in a production environment is where you have very, very old Cisco switches that need to interoperate with something newer. Now, all of these three are mentioned in brief in the Cisco exam series, but unsurprisingly, the only one that is mentioned in the Network Plus or the Juniper exam is per VLAN spanning tree. And then another couple, because of course there are more IEEE standards to play with. There's one called rapid spanning tree. I mentioned that earlier. Essentially cuts the time that it takes a network to form from about a minute to about 2 seconds. And there's multiple spanning tree, which essentially allows a version of per VLAN spanning tree to take place. You really don't need to know anything about these from an exam point of view. It is useful to know that they exist, and rapid spanning tree in particular, you will find in many production networks because a 2-second network outage is a lot more tolerable for most businesses than a 1-minute outage is. Broadly speaking, you can configure them in the same way. Now, how does spanning tree actually do its thing? First of all, one of the switches, one of the bridges, is elected as the network root, the top of the network, if you will. Root ports are identified. They're ports on the downstream switches that are topologically closest to that switch. And there's a diagram very soon, so I'll walk through that in just a moment. And then there's designated ports, which are the reverse of the root port. And where there's more than one potential root port, one of those will be selected to be disabled. Because if there's two ports that are equidistant on the same switch, that's a loop by definition. And if there's multiple loops, the switches will select multiple ports to shut down and switch off. They'll re-enable them the instant that there's a problem with the network and not before. So root bridge is always the first thing selected. Generally speaking, the bigger and more expensive the switch, the more likely it is that it will select itself as the root bridge, but you can adjust that using configuration, using what's called a bridge ID. You can adjust the bridge ID using a switch priority. And generally, what vendors do when they're making switches is they're more expensive and more powerful models. The kind that you would typically use in a core of a network will have lower, smaller MAC addresses than cheaper edge switches will. That in turn means they will tend to naturally win such root bridge elections, but you can force the issue by changing the switch priority. Root port points to each switch. Each points to the root bridge essentially, or has the shortest path to it, but each switch can only have one root port. And the root bridge, of course, it is the root bridge. It can't have any ports that face the root port. Now, root ports are selected based on bandwidth. So if you have two links that face towards the core of the network, and one is a 10 gigabit link and one is a 40 gigabit link, the 10 gigabit link will lose and be disabled as a backup link. In the slides, there is this table, which allows you to figure out what the default values are for the different link speeds and the typical behaviors that we would see. Okay, so I promised a diagram. I'll walk through what this diagram means. I will highlight that the colors don't mean good, bad, or otherwise. They are just colors. Now, in this case, the switch at the top here happens to have been selected as the root bridge. So it's essentially, for the purposes of this network, the core of the network. Now, in that case, it's got three designated ports on it. The designated ports are the green ports that face away from the root bridge. The red ports are the root ports. You'll notice on this switch, you've got two links that face upstream. And in this case, it's determined that the root port happens to be 1023. So the other port becomes a non-designated port and gets shut down automatically. Now, if something happens to this link will automatically take over. The standard spanning tree, that process will still take 1 minute, but it'll at least happen, and it'll happen without human intervention. And all of these other links then will basically fall out of that same topology. So you'll see here, we've got a couple of different loops in the network. There's a loop here, there's a loop here, and there's a loop here. That in turn means that this link, you'll see this one's also gone yellow as a non-designated port, and will also be shut down to prevent that loop, as will this link. So essentially in each case, it'll just pick the shortest possible logical path back to this switch, and any links that don't help get to there will just be shut down. Probably a good time to take a pause and ask any questions.
Well, we've certainly got a few questions there. Would you like to select one, or would you like me to select one for you?
If you'd like to select one, we'll start with yours and we'll work backwards from there.
Absolutely. So an anonymous attendee has asked, how does the STP function as a primary control mechanism in computer networks? To what extent is that effective in preventing looping issues that could disrupt stability and data flow efficiency?
That's an excellent question. I love it. So essentially, from a network control perspective, spanning tree's main and indeed only real purpose is to prevent loops and therefore assure the network's ability to carry data. How effective is it at preventing loops? Pretty efficient, really. That is its job. That's been its job since I think the earlier versions of the standard were the late 80s, basically when switches first came onto the scene in any meaningful way. And there's a reason it's hung around as long as it has. It works. It does what it says it does on the tin, and meets that requirement. In a modern network, it's not necessarily the best possible way to go about things. As I said, it isn't fast to make these decisions. It works on the presumption that you're going to need about a minute to identify loops. And that comes out of the fact that, a switch from the early 90s didn't really have a lot of compute power. If you think about the kind of desktop computers we had in the 1990s and think about what the average microcontroller looks like, essentially spanning tree had to work with that. You know, if you had a switch with a 386 processor in it back then, you were probably doing incredibly well. These days, of course, it's not uncommon for a modern switch to have a lot more compute horsepower. So, of course, there are better ways to improve stability, to improve availability, since obviously any outage, even if it's to avoid a loop, is bad, then all the better.
All right, and I think I'm gonna unfortunately have to keep you to one question there, just for time reasons. But thank you very much for that.
Yeah, no problem. Let's keep going. Okay, so spanning tree, and you'll see these states on the previous slide. There's 4 different states that come to play. There's the blocking state, where the switch won't actually learn any client MAC addresses. The only frame it's looking for is that bridge protocol data unit, i.e. it's listening for other switches, so it can figure out for itself what lives where. Then there's listening, which is a state that it goes through to try and identify that there are other switches out there. There is a low risk of a loop, but we're not 100% certain of that state just yet. Then there's learning, where we're now listening for MAC addresses. We're now learning what the network looks like overall. We've got a pretty good idea of all the switches are. Now we're starting to wait for PCs to wake up as well. And then there's forwarding, where the switch does what switches should, which is send traffic from A to B and beyond. Now there is actually a 5th, but it's not actually part of the standard. Every vendor does it, but basically it's called disabled, where the switch is shut down, or where the port is shut down on that switch. Timers, I said it's very, very slow. Spanning tree can take a minute or more. So by default, the switches will talk to each other using what's called a hello packet or a hello frame every 2 seconds. So they'll continually talk to each other, and to sort of partially answer one of the questions that someone asked before, that's how a switch determines when there has been a problem, such as a link breakage, or what in the terminology of the standard is called a topology change.
Sorry, Ian, are you able, just for back-end reasons, to just click to finish your having answered that question?
Sorry, which one? Oh, yes, sorry. Yeah.
Thanks very much.
Done. Sorry about that. Yeah, so first of all, when a switch wakes up and connects to a network, we have a topology change that occurs. That 2-second trigger basically allows that switch to identify within 2 seconds that there has been a problem. After that, it's going to pause for 15 seconds to listen to the network, figure out where all the switches are. It'll then pause for a further 15 seconds. So we're already up to 32 seconds to figure out what devices are connected where. And then there's an aging timer, which adds another 20 seconds to that before the switch will actually start forwarding traffic. So changing these should only be done in one place, in the core of the network. It's important to know that if you change it elsewhere, it can cause all sorts of configuration challenges. And indeed, in the CCNA exam, there is, or was in the past, a question related to that misconfiguration. But long and the short of it is, spanning tree is designed to take a very long time to figure out what the network looks like. Now, when can a topology change occur? In other words, when can the switches decide they need to reassess their situation? That'll happen if you plug in a new switch. It'll happen if you plug in pretty much anything that can communicate on a network. Now, that's obviously not a great situation, because it theoretically means somebody plugs in a new PC, you could bring down the whole network. Now, I'll talk in a couple of slides about some ways around that. But essentially what happens is the switch says, hey, something's changed locally to me, sends that up to the root bridge, and the root bridge goes out and says, all right, everybody, let's go and have a look at this again. And all the switches will essentially shut down all communication and go through the whole blocking, listening, learning process again in order to figure out what the network looks like. And this is, bear in mind, this is all because of the catastrophic effect that a loop will have on the network. And at the time that the standard was built, dealing with loops was far more important than, dealing with the occasional minute-long outage. There's a few different ways. I mentioned earlier that if you plug in a PC, theoretically that can cause a topology change, which can shut down a whole network. There's a standard extension called port fast, which essentially allows a switch to say, right, the only thing that is ever going to be plugged into this port is a PC. There's no possibility that somebody's going to plug in a switch, and therefore I don't need to worry about whether there's a risk of a loop. So port fast is a common configuration element to use to prevent such things occurring. Then there's uplink fast, which basically says the only thing that's ever going to be plugged into me is a switch. Therefore, there is a risk of a loop, but hey, I know about that, so I don't need to take the first learning and listening steps. I can just shortcut the process and start looking straight away for loops. You can't do that on the root bridge, but you can do it on downstream switches. And essentially, again, you're giving in configuration the switch a hint about its actual location in the network. And then there's backbone fast, which I've only ever seen in one network configuration. But essentially it's used where you've got a couple of different switches that are connected by less direct mechanisms, such as connected through a service provider or carrier network. So that's not covered in the exam, but the previous two are. Other mechanisms that can be used to prevent loops while still using spanning tree. There's the concept of root guard, where you can effectively enforce a root bridge as being the root bridge. There's BPDU guard, which with port fast is essentially the corollary to port fast, which is if you're saying this can only ever be connected to a PC, you can configure the port such that if it does see evidence of another switch existing on that port gets shut down straight away. And sure, that affects that PC, but it stops any loops from occurring. And that's quite common in large corporate and even university type networks, because people can and do often bring in their own switching devices. You want to try and stop that. And then there's filtering, which essentially tells a switch to lie about its status and become a PC instead. Okay, we're at the VLAN section. So that's the end of spanning tree. Before I get into VLANs, do you reckon there's any questions, or should we just keep churning through?
There are several questions. Up to you whether
Awesome.
you would like to. We're right on time.
Okay, cool. Well, let's answer a couple anyway. We'll see how we go. So I'll start with Craig Mills's question, which is how a root bridge is elected. So there's two components to the mechanism that a root bridge is used. The first is what's called a root bridge priority, which is a number between 32,776 and 0. Lower is better. That you essentially manually configure on the switch. So if you've got a particular switch that you do want to be the root bridge, you can set that number very low. The other part of it, so both of these elements are used in conjunction with each other, is the MAC address. The MAC address is essentially converted into a number because, well, that's fundamentally what it is, and the smallest number wins. Mauricio asks which type of spanning tree is the most effective. One of my favorite answers I ever give is that depends. But generally speaking, these days, you're going to see rapid spanning tree used in a spanning tree network because it will do its thing within about 2 seconds. So while you'll still get a network outage when a link fails, it tends to be limited to 2 seconds instead of about a minute. Michael Lloyd asks, will spanning tree work between different branded switches? Absolutely, yes. That's the whole point of them being standards, is that they should be well supported. And Stephen asks, I assume in spanning tree after the failure is fixed, the block port is disabled again and blocked again to break the loop? Absolutely, yes. Cool. All right. We will keep. Oh, I will answer Joshua McFarlane's question because the quick answer for that is OSPF is a layer 3 discussion predominantly, and we will be talking about OSPF next week. Cool. Now we get on to VLANs. Okay, so you have a large network. You've got, let's say, I don't know, you're running a large campus network at a large university. You've got potentially, several hundred devices in a building. Let's say you've got 2 different faculties in the building, and you don't, either for security reasons or even just simply for management purposes, don't want their traffic to interfere with each other. Now, there's a couple of ways you can do that. You could, in theory, deploy 2 entirely separate networks. You could, wire the building accordingly. But then what happens when inevitably people move rooms? There's always a little bit of that sort of flux. How do you send someone out to rewire the room? Do you, physically move a switch from one location to another? Well, you could, or you could use the concept of a virtual local area network. So what a VLAN does, a virtual local area network does, is essentially allow you to have multiple logical networks, multiple logical layer 2 networks on the same physical devices at the same time. So essentially it allows a switch, which we've already described as having a single broadcast domain and multiple collision domains, to also have multiple broadcast domains. Now, you can use a multi-layer switch, which becomes a router as well, but that's not a requirement. You can have a layer 2 switch that speaks VLANs, which in turn means that those 2 VLANs in that case pass like ships in the night. They have no ability to see each other or communicate with each other. So a good example here, say you've got this network, you've got a switch, you've got 4 different PCs, 2 PCs belong to one business unit, the 2 PCs belong to another business unit. How can you separate them? You separate them by putting 2 on a VLAN that we'll call VLAN 1, and we'll put the other 2 on a VLAN that we'll call VLAN 2. You'll note that the IP addresses in question are from separate networks. And essentially, it's the same as if you had 2 physical switches with 2 separate sets of network cabling to each. The difference is if all of a sudden computer C needs to be moved to VLAN 1, it's easy to do. You don't have to send somebody out to plug in and unplug a cable or anything. You can simply reconfigure the switch and give this PC a new IP address. Why would we use them? Well, for one, we've already talked about broadcasts a bit tonight, but if you've got a very, very large network and it's all layer 2, every device on that network is going to be listening to lots and lots of broadcast traffic. VLANs allow you to manage that a little bit. You can essentially, if you double the number of VLANs, you can halve the amount of broadcast traffic per VLAN. It does give you some level of security. It is important to note that there is some possibility of breaking VLANs, but generally speaking, it allows you a certain amount of isolation between 2 devices that are sitting side by side. And as well as that, it gives you that ability to move people and devices around and not have to worry about what the actual cabling looks like. As long as the switch can see the VLAN, then the device can use that VLAN. There's 2 different ways you typically manage VLANs. First is each port gets configured manually. The other way is to use various types of dynamic allocation. The only thing the exams cover is the static version, where you essentially configure a device port by port by port and allocate each port to a specific VLAN for a specific use case. And a lot of the work in a typical large operational network will be that sort of add, move, change, where somebody's moved rooms and the VLAN needs to move with them. Within VLANs, there's two different types of ports. There's what Cisco determine as an access port, and what the standard, the 802.1q standard, talks about as an untagged port, which is essentially a port with just one VLAN on it. So that's the default state. That's the original version of a switched network. Now, there are exceptions to the single VLAN rule, though. If you've ever dealt with voice, or if you've ever seen a Cisco phone sitting on a desk, they typically use what's called a voice VLAN, which is a special case of an untagged port that will accept traffic from that phone specifically. Cisco then talk in terms of trunk ports, which the standard calls a tagged port, and essentially allows for multiple VLANs to coexist on a single VLAN, on a single port. So you can have, rather than stringing multiple cables between a switch and the core, you can just run a single cable and put all of your VLANs over that single cable, using essentially different forms of labeling to identify that. Now, that only works for ports above 100 megabits per second. That is mentioned in the standard. Not quite sure why, because it's very hard these days to find a device that has a port slower than 100 megabits per second. But certainly on higher speed links, you're more likely to see trunked or tagged port configurations in any case. Here's an example of where you might use VLANs. On the left, you've got essentially access ports or untagged ports with multiple physical cables running between the switches. And that would be logically the same as having 3 different switches at each level for a total of 9 switches with 3 completely isolated networks. Pretty inefficient. So the other way you can do it is essentially to aggregate those VLANs onto a single trunk or tagged port and carry that data down between the switches in exactly the same way, and let the switches worry about separating it back out at the other end, which is what they do very well. So how do we do all of this on a trunk port or on a tagged link? We use what's called frame tagging. So layer 2 frames typically have a source and destination MAC address. The standard, the 802.1q standard, adds to that a bunch of additional information, including what's called a VLAN identifier. And that VLAN identifier essentially associates that particular frame to a particular virtual local area network. And the switch at the receiving end goes, great, wonderful, pulls all that information out and sends the traffic on to where it needs to go. And tagging only happens at the trunk ports. Edge devices don't need to know or care about it, because that's the only place where you're actually dealing with more than one VLAN. So a bit of a more complicated example than the one before. You maybe want to get computer 1 over here talking to computer 5. That might be on VLAN A in this case. You might want computer 4 talking to computer 7 on VLAN B. Now, you've only got a single physical cable here, but both VLANs are carried separately. I've just represented using colors here, and apologies for anybody who's colorblind, red-green colorblinded, can't see that. I'm more than happy to adjust that if needed. In any event, essentially from the network point of view, it's one physical topology with 2 switches, but from a logical point of view for these devices in question, it's as if they have completely separate infrastructure. So computer 1 doesn't need to know anything about VLANs to talk to switch 1. Switch 1 adds VLAN A on that link to switch 2, and then computer 5 doesn't need to know about it because switch 2 removes that information. Same for computer 4, no VLAN is needed at that point. VLAN B is used, and then that information is removed when it goes onto the computer at the end, computer 7. There's 2 different standards. If Cisco do something well, it's create their own version of standards. There's a version called InterSwitch Link, which obviously is covered in the CCNA material to a degree. It's not very common. You don't generally see it. And then there's IEEE 802.1q, which is absolutely a standard. It's very well supported. Many PCs and certainly all servers do support it as well. So you can actually tag traffic all the way down to a computer if you really want to. And it's very, very, very well supported. It's also very, very heavily covered in all 3 exams that you might choose to do. Now, of note, it supports up to 4,094 VLAN IDs. And in pure terms, that means that you can have up to 4,094 virtual networks in any given physical environment. And I've just put a bit of a stretch goal that people might want to put an answer to in the chat. There is a version of 802.1q called Q&Q. And if you want to put your guesses as to what Q&Q might do, and a rough guess on the number of VLANs it might support if such a thing exists, I'd be very interested in reading them later as well. Before I move on, any questions worth covering?
Up to you, we've got time.
Yeah, okay. So Jacques asks, will a switch accept any traffic even if it does not have a MAC address in the table? So it'll accept any traffic to a valid MAC address, even if it doesn't recognize that MAC address. Its behavior, if it doesn't recognize the MAC address, will be to forward the traffic as if it was broadcast, to send it out every port except the receipt port. Should trunk have an access VLAN as well? That's a really good question, Greg. I will answer that very shortly. The long and the short of it is, there is this concept of a native VLAN, and that is the way a switch will deal with traffic that is untagged. David asks, if you're running Teams or similar, is it necessary to run a voice VLAN? The short answer is no, it is not. The longer answer is it's always advisable to follow the advice of the vendor in question. Some vendors will recommend a voice VLAN for quality of service reasons. Some will not. Cool. All right, so trunking, which is another word for tagging. .1q tagging, like a lot of things, like assigning VLANs in the first place, in fact, you can do it manually, and that is the default. That is the usual way to do it. So you can define the VLANs that a switch recognizes and then further define which VLANs are carried on which ports, including on trunk ports. Or you can use protocols to do that work for you. Cisco invented a protocol called DCP, Dynamic Trunking Protocol, which allows switches to automatically learn from their upstream neighbors what VLANs live where. And then there's VLAN Trunking Protocol, which essentially not just tells the switches what VLANs are in use, but actually gives them some data and information on those VLANs. Now, both are generally deemed to be a bad idea these days for security reasons, because they do share a lot of information about the network. And while security through obscurity is never a good approach, it's still not a good idea to share more information about the configuration of your network in a way that a third party could potentially capture off the network. So generally speaking, it's better not to use those protocols, but if you do choose to use them, they do make configuration of the network much easier. So it's the age-old security versus utility discussion. You know, if you choose to use it, you're potentially trading off a little bit of security to gain that utility. The native VLAN. So this is exactly the question that was asked earlier. So generally speaking, there's a native VLAN called VLAN 1. By default, at least, that's what it's called, which is not tagged when it's sent on a trunk port. So essentially any traffic that comes in that is not tagged is automatically assigned by the switch to VLAN 1, unless you configure it otherwise. Now that can be a source of misconfiguration. Let's say you've configured the native VLAN on one side to be port to VLAN 20 and on the other side VLAN 40. It means that those switches, when they receive traffic that is not tagged from each other, they're going to potentially bridge that traffic between VLANs. Now, in turn, it is possible to create loops that way that even spanning tree won't save you from. So it's a really good idea to make sure that all of your network is configured consistently in terms of the native VLAN. But at the same time, it is really good practice to change away from VLAN 1 so that some common security attacks such as VLAN hopping have less chance of success. And that is the end of tonight. So any questions that are worth catching up on?
Incredible timing. I will let you select your own questions now that we're
Awesome.
not pressed for time.
No worries. Okay, so Tom asks, does Cisco support the IEEE standards as well as their own? Generally, yes. They are a very good participant in the standards world. They do participate in the standards bodies as well. They do unfortunately have a habit of creating their own variants from time to time as well. And that can cause much frustration amongst other vendors as well. But yeah, credit where credit is due. They are, good players in the securities in the standards space. What happens if a device on VLAN 1 wants to speak to a device on VLAN 2? Asks Adam. That's where layer 3 comes in. So that's an excellent segue to next week. So essentially, VLAN 1 and VLAN 2 require routing to work. Bijal asks, do switches that support port fast label a port as port fast for easy identification? That's an excellent question, and I foresee a role for you in an operational environment in the future. Unfortunately not. Port fast does appear in the configuration of an appropriately configured switch, but generally speaking, how it's labeled in terms of port descriptions and the like tends to be something that needs to be handled by the operations team, whatever that looks like in an environment. So a lot of people will put things in the port description that will appear in any network management tools to identify when a switch is when a switch port is port fasted. So just trying to see. There's so Greg asks, is there a general sizing guide for IP management per VLAN? So the best practice guide for layer 2 and layer 3 networks is to minimize the size to sort of around 250-ish hosts is a good upper size limit for a layer 2 network. And conveniently enough, that actually ends up being about the size of a /24. That is a what used to be called a Class C IPv4 network. Anything much bigger than that starts to get a bit unwieldy, and obviously smaller can be better. The trade-off, though, is that the smaller your IPv4 network is at that space, the more space you're going to lose to the network and broadcast addresses within each IPv4 network. Okay. Gemicus asks, does every managed switch have spanning tree? I can answer this confidently that the answer to that is not every managed switch supports spanning tree. Many do, but I can't certainly speak for vendors like D-Link as such. But as a general rule, cheaper switches may not support that feature, even if they have some level of management. But that's not a blanket rule. There are plenty of sort of SMB type switches that do support spanning tree very, very well indeed. Okay, I think that's probably. Oh, actually, there's a question that's worth that's absolutely worth picking up on. Can a port in a MAC address table be associated to multiple devices? Absolutely yes. So if you look at a trunk port or a tagged port, for example, it's going to learn every single device that might be connected to the downstream switches. That same fact means that port might see hundreds or even thousands of MAC addresses that aren't physically or directly connected to it. So yes, it's absolutely possible for a MAC address table to show multiple MAC addresses per port, but one MAC address will only ever exist in one location on one port. So you can have multiple MAC addresses on a port, but that MAC address can only exist on one port. Cool. I think that's about all I have time for, to be honest.
Fantastic. Thank you so much. I think that's a great place to leave it. And if anybody has burning questions or even non-burning questions relevant to the topic that weren't able to be answered tonight, feel free to check out those student forums on learn.itmasters.edu.au, where you can discuss with one another as well as with Ian the answers to some of those questions and learn from each other's experience and expertise as well. That learn.itmasters.edu.au portal is also where you will find all of the materials for the course. So that is last week's webinar, this week's webinar at some point in the next 24 hours, next week's webinar in approximately 1 week. As well as any additional materials, quizzes, etc. So please jump on there and have a look at everything. Thank you very, very much, everybody, for attending. As always, if you're interested in signing up for any of our full-length graduate certificate or master's degrees with ITM and CSU, you can jump onto our website at itmasters.edu.au or send us an email at eligibility@itmasters.edu.au to find out if you are eligible to enroll in one of our full-length courses. Of course, if you complete successfully 3 of these short courses, that does count as 1 subject worth of course credit towards your full-length course. So great incentives there. As always, thanks very much to Lily Nguyen for making sure that everything has been running smoothly in the background. And thank you, Ian, for being such an engaging and informative mentor.
Not
thanks,
a problem.
everybody. Not a problem. We'll be back here, same time, same place next week. That will be next Wednesday at 7:30 p.m. Australian Eastern Daylight Savings Time. And in the meantime, enjoy learning more on the student portal. And depending on where you are in the world, good morning, good afternoon, good evening, or good night. Thanks, everybody. Have a great time.